Hi, I'm Maarten Visser. Welcome. This is part 4 of the Woodwind Adaptive Instrument Design Series. And this is about calculations on key arms. It's a bit technical. If you don't have to watch it, you can skip this.
How do you calculate a simple key?
Let us say we have this simple key. Here is a drawing, a cross-section that are made in Rhinoceros CAD software. So the length to the pad is 21 millimeters, and we measure that length from the center of the hinge, from where it moves, to the rim of the tone hole, because we're interested in how far the pad opens if we move the key. Typically, the venting, so how far the pad opens, is a quarter of the tone hole diameter, especially on larger instruments. On smaller instruments, like recorders or oboes, it can be as large as half of the tone hole diameter. So, in this case, we have 3 millimeters. So, how far will the touch piece move? For the sake of the calculations, we make all the lengths variables. So it looks like this in the formulas. And this is what the calculation looks like. So the term b divided by a can also be expressed as the tangent of the angle. For high precision, you would be using actual angles. But with these small angles, we can use this calculation. It's perfectly right for our purposes.
Can you do the same calculation on the key interaction?
Yes, we can and we should, because we have to know exactly how much the keys move and how much, and where to place the levers and how long they have to be. It's not too difficult, really. Here's the drawing, and you see the names of all the variables. So what happens if you push the lever? This key closes. So the extra rotation inverts the action. So in the previous example, we opened the key, now we are closing it. Something more to note is that the effective lengths of the levers A2 and C2 is to get at the distance between the pillars. So if you move the contact point to one side gets longer and the other side gets shorter. But the total stays the same. Levers are always longer than this, but we are now calculating the contact point. As you see, the variable D2 is in the formulas, in the equations, but it's not in the drawing because it's the same as B2. One lever moves, for example, 2 millimeters, the other one also moves 2 millimeters. So are the same, they are the same. And we use that property to calculate the whole thing. Because if they are the same, one minus the other will be 0. So we put everything into a spreadsheet like this, and we just fill in some value for A2, which is one of the levers. We know B2 is D2, like we said before, that sum must be 0. It's the last term on these equations. And we just iterate to find the right numbers. Or we can let spreadsheet do the iteration. So here we find lever lengths for A2 becomes 11.6 millimeters. C2 becomes 10.4. It is solved.
It does not get more complicated than that, does it?
I'm afraid it does. especially when you get into octave systems. But here I have something different, a bit more complicated, but very useful in making adapted instruments. That's a parallel bridge link of my own invention. So here we have key number 2 that we want to open. We now want to close it using key number 1. Key number 1 moves anti-clockwise. So both keys have an arm, and these arms are connected with a small screw using bridge arm A. So bridge arm A connects the keys. If one moved, the other will move too. If you, in a close-up, you can see the movement of key number 1, and that movement will also change the position of the bridge link. Now it's rotating, so where can it go to? The red circle defines the range of motion of bridge link A. So turn over. Key number 2 also has a limited range of movement because it's rotating around the hinge. And the contact point with the bridge link is defined by the black circle. And you see the black circle and the red circle, they intersect. I made a little arrow there, and that is where key number 2 will move. And thus key number 2 closes. So to design such a system, you make a drawing and you make a line, a long line that goes through the centers of the movement hinge, and the arms for the bridge link, the arms sits exactly square on that line. The mathematics of the length of the arm is exactly the same as in the previous example. Also here on this example we had different opposite directions, but you can also make these arms move in the same direction. You just have to flip one of the arms. Here's an example. It's a thumb key for a flute, designed by me, built by Charlotte Havers. The S-shaped levers here is exactly like bridge link A in the example. So this is the alternative flute thumb key. This is the B key, and this is the B flat key. Here the arm is moving, this is the arm, and here the B flat is closing. Here is an example on a saxophone. It's a construction in which the two hinges, they rotate in the same direction, and in this case the tone hole is opened by some action somewhere else on the instrument. These hinges are sort of parallel, but not exactly, because the body of the instrument is tapered. So to stop the bridge link from binding, from not functioning anymore, there must be a small bit of sideways rotation, and that's why I introduce these ball joints. It works perfectly well and with very little friction. I hope you enjoy this video. If you have questions, please post them in the comments. The next video is about the technical methods for physically constructing the keys on the adaptive woodwinds. Thank you very much for watching. Bye bye.